Have you ever stopped to think about how your computer finds one single file out of thousands? Or how a search engine just rifles through billions of pages in like less than a second? Well, it all comes down to the strategy it uses. So let's get into it. We're going to break down two of the most fundamental search algorithms out there, linear and binary search. To really get a feel for this, just imagine you're in a library, a huge library with a million books. But here's the catch. They're in no particular order. Total chaos. How would you find the one specific book you need? You pretty much have to start at one end of the library and look at every single title until you hit the jackpot, right? Well, that exact headache is a problem computers deal with all the time. So in the world of computer science, we call this the search problem. It's this classic challenge of having a massive collection of data, a digital haystack, and needing an efficient way to find that one specific piece of information, our needle. Whether you're looking for a contact in your phone or a product on Amazon, it's all about the search. To solve this problem, we use algorithms, which, is really just a fancy word for a step-by-step recipe. And there are a ton of different ways to search, but we're going to focus on two of the most foundational methods that, honestly, every programmer has to understand. First up, we've got linear search. Now, this is the most intuitive, most straightforward approach you can imagine. It's exactly what we talked about in that messy library, just checking things one by one right down the line. So the key takeaway here is that a linear search just methodically works its way through a collection, item by item, from the very beginning to the very end. It doesn't make any clever assumptions about the data, it just powers right through it. And the process itself? Incredibly simple. You start at item number 1, and you ask a really basic question. Is this what I'm looking for? If the answer's no, you just move on to the next one, and the next, and the next. You just keep repeating that simple check until you either get a yes, or you just plain run out of items to look at. Now here's where it gets interesting, how we measure its performance. With a linear search, the time it takes to find something is directly tied to how many items are in the list. So if you double the number of items, you can pretty much expect the search to take, on average, twice as long. It's a one-to-one relationship. And we have a special name for this relationship. It's called Big O notation. A linear search has what we call a time complexity of O(n). That's big O of n, where that n just stands for the number of items in the list. It's a totally linear relationship. The work grows in a straight line right along with the size of the data. But what if we could be smarter about this? What if there was a more clever, more efficient way to search? Well, that brings us to our second algorithm, binary search. And this, my friends, is where things get really, really fast. But there's a catch, and it's a huge one. This is one of the most important trade-offs in programming. Linear search, our simple friend, it can work on any list, doesn't matter how messy it is. But for binary search to work its magic, the data absolutely must be sorted. Alphabetically, numerically, whatever. It just has to be in order. No exceptions. This is what we call a divide and conquer strategy. Instead of checking one by one, binary search jumps right to the middle of the list. Think about looking for a word in a physical dictionary. You don't start at the A's, right? Of course not. You crack it open somewhere in the middle, see what letter you've landed on, and you instantly know whether your word is in the first half or the second half. Let's actually see how this works. We're looking for the number 25 in this sorted list. First, we check the middle element, which is 15. Well, 25 is bigger than 15, so we know our number has to be in the right half. So boom, we can completely ignore the entire first half of the list. Just like that, half our work is gone. We then repeat the process on that smaller remaining half, and within just a few steps, we've completely zeroed in on our target. Because we're cutting the problem in half with every single step, the performance is described as logarithmic, or O of log n. And this is an absolute game changer. It means that even if you double the size of your list, it pretty much only takes one extra step to find what you're looking for. The power of that is just incredible. Okay, so we've talked theory, O of n versus O of log n, but what does that actually mean in the real world? Let's put these two algorithms head-to-head and see what happens in a speed test. How much faster is smarter, really? Are we talking about a few seconds? A few minutes? Let's make this really tangible. Let's use a great example from our source material. Picture a list, a huge one, with 600,000 words in it. Our job is to find just one specific word buried somewhere inside. Okay, so if we use our simple linear search, checking one word at a time, this task would take, wait for it, 166 hours. That's almost a full week of a computer just chugging along, checking words one after the other. Insane, right? Now, for binary search. On that very same list, assuming it's sorted alphabetically, of course, it would find the word in about 20 seconds. Let that sink in. The difference between nearly a week and the time it takes to grab a coffee. Mind-blowing. And this graph shows you exactly why. That steep line shooting up towards the sky, that's our ON linear search. As the list gets bigger, the time it takes just explodes. Now look at that flat little curve hugging the bottom. That's our hero, O log n, the binary search. It barely even seems to rise. As our digital haystack gets bigger and bigger, the performance gap becomes absolutely astronomical. So the answer is obvious then, right? Binary search is always better, case closed. Well, not so fast. Choosing the right tool for the job is what programming is all about. And believe me, there are always trade-offs to consider. This table sums it all up perfectly. If searching is what you do most of the time and your data is nicely sorted, binary search is the undisputed champ with its O log n speed. But look at inserting new data. In an unsorted list, you can just tack a new item on the end. That's super fast, what we call O1. But to insert an item into a sorted list, you've got to find the exact right spot and then shift everything else over to make room. That's slow. That's an ON operation. So here's the bottom line. Linear search is simple, and it's your best friend for small lists or data that's just a total mess. Binary search is lightning fast, a total powerhouse, but you have to be willing to pay the price of keeping your data sorted. And that cost of sorting, that's a really crucial factor. And that leaves us with one final thought. Think about all the apps on your phone, the websites you visit every day. When you search for a song, a friend's name, or a piece of news, what's really happening under the hood? Based on everything we've just seen, which algorithm do you think they're choosing and why? The answer is, it always depends.